This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the area between curves. Our goal in the first problem is to find the area between the functions f of x equals 2x plus 1 and g of x equals the square root of x on the interval from 0 to 4. So we can see these two functions. 2x plus 1 is the linear function. That one is the one that's on top. G of x equals the square root of x is the one that's on the bottom. We're interested in the interval from 0 to 4. So we could take the integral from 0 to 4 of 2x plus 1 to get all of the area underneath 2x plus 1. Then we could subtract the integral from 0 to 4 of the square root of x to subtract this area here to be left with the area in the middle. So indeed, integral of the first function minus the integral of the second function, or integral of the top function minus the integral of the bottom function, will give us the area in between. But we can simplify that and just take the integral of the top function minus the bottom function. And that's in general how we're going to approach the area between functions. In this case, the top function is obvious if we graph it. The top function is 2x plus 1. And the bottom function is the square root of x. So the area between this area in purple will be the integral from 0 to 4 of the top function minus the bottom function. 0 to 4 of 2x plus 1 minus the square root of x. Now before we continue, let's take a look at that graph and let's approximate what that area should be. You'll notice each one of these boxes is 1 by 1, so maybe these two together is about 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe around 10, 11, 12, 13, 14-ish. So it's not a bad idea to kind of eyeball that area in between to see if the answer that you get is close to your prediction. So we're just by counting boxes, we're going to predict it's about 14. But again, remember the integral for the area is the integral of the top function minus the integral of the bottom function. Integral of the top function 2x plus 1 minus the bottom function root x, integrated from 0 to 4. So that's what we have, and we have to go ahead and simplify that integral. Well, 2x plus 1 minus root x is just 2x plus 1 minus root x, so that's nice and easy. And then we've got to go ahead and find the antiderivative. But let's rewrite square root of x as x to the 1/2 power. That will make that a little bit easier for us to evaluate. The antiderivative of 2x is x squared. The antiderivative of 1 is x. The antiderivative of x to the 1/2, let's see, kick x to the 1/2, kick the exponent up by 1, 1/2 plus 1, x to the 3/2 over 3/2 is what we're going to get there. So again, antiderivative of 2x, x squared, antiderivative of 1 is x, antiderivative of x to the 1/2, x to the 3/2 over 3/2. But dividing by 3/2 is the same as multiplying by 2/3. We've got to plug in 4 and 0 and subtract is what we're going to need to do. So plugging in 4 squared plus 4 minus 2/3 times 4 to the 3/2. Plugging in 0, 0 squared plus 0 minus 2/3, 0 to the 3/2. Everything here becomes 0. 4 squared is 16, plus 4. 4 to the 3/2. Do the square root of 4 first. 4 to the 1/2 is 2. 2 to the third is 8. That'll be 2/3 times 8. So 16 plus 4 minus 2/3 times 8, that's 20 minus 16/3, which gives me 44 over 3. Now what is 44 over 3? It's about 14 and 2/3. So our eyeball prediction of 14 was pretty good. So it's a nice way to kind of see if your answer is reasonable. Okay, let's take a look at another question. We want to find the area between the functions f of x is x squared minus 4 and g of x is 3x. We certainly could graph these and we could visualize it that way, but I'm going to take a slightly different approach here. First, I want to find the points of intersection. So the points of intersection will be when this function, x squared minus 4, equals this function, 3x. So subtracting 3x from both sides, x squared minus 3x minus 4 is 0. And that will require us to factor that trinomial. X minus 4 times x plus 1 is 0. Setting each one of those equal to 0, x minus 4 is 0, or x plus 1 is 0. So adding 4 to both sides, x is 4. Adding -1, x is -1. So we have a line and we have a parabola, and they intersect when x is -1 and when x is 4. The next question I want to ask is, which function is on top? Again, we could get that immediately by graphing it, but I want to do some analysis here to see if I can figure it out. So between -1 and 4, let's pick a representative number between -1 and 4. 0 would be the easiest one to try, but any one will work. If I plug 0 into this first function, f of 0, 0 squared minus 4 is -4. Plugging 0 into this function, g of 0 is 3 times 0 is 0. So let's visualize this. They intersect at -1 and 4, but f of 0 is -4, g of 0 is 0. G value of 0 is higher than the f value of -4, so g is the function that's on top. 3x is the function that's on top. And no surprise, a parabola opening upwards in a straight line where they intersect, the line will indeed be on top. So I'm going to integrate from -1 to 4 of the top function, 3x, minus the bottom function, x squared minus 4. -1 to 4 of g of x minus f of x dx, -1 to 4 of 3x, top function, minus x squared minus 4. And again, we can see all of that if we graph it. We can see the points of intersection. We can see which one is on the top, which one is on the bottom. So indeed, here is our graph. Clearly, 3x is on the top, x squared minus 4 is on the bottom. And you could use the graphing applications to find out where the points of intersection are. But they are indeed -1. X is -1 here, and 4. X is 4 there. So integral from -1 to 4, top function 3x minus bottom function x squared minus 4 will give us this area between those two curves. So this is my integral. Now be careful. 3x minus x squared minus 4 requires us to distribute that negative sign. 3x minus x squared plus 4 minus -4 plus 4. And then we want to find the antiderivative of each piece. Evaluate from -1 to 4 and subtract. The antiderivative of 3x would be 3x squared over 2. Antiderivative of x squared would be x cubed over 3 using the power rule. Antiderivative of 4 would be 4x. So 3x squared over 2 minus x cubed over 3 plus 4x evaluated as x ranges from -1 to 4. We're going to plug 4 into all of this, subtract, plug -1 into all of this. Plugging in 4, 3 times 4 squared over 2 minus 4 cubed over 3 plus 4 times 4, as we'll see here. Plugging in -1 to all of this, 3 times -1 squared over 2 minus -1 cubed over 3 plus 4 times -1. All right, 4 squared is 16. Times 3 is 48, divided by 2 is 24. 4 cubed is 64 over 3. 4 times 4 is 16. Over on this side, -1 squared is +1. This will be 3 over 2. -1 cubed, -1 times -1 times -1 is -1. It'll be minus -1 over 3. And 4 times -1 is -4. As we see with all this, 3 times 16 over 2, 64 over 3 plus 16 minus 3 times +1 over 2 minus -1 over 3 plus 4 times -1. You can certainly do this on the calculator, or we can do a little bit of the arithmetic. 16 over 2 is 8. 3 times 8 is 24. That'll make my life a little easier. Minus -1/3 would be +1/3. So we'll make those changes. 24 and 16 is 40 if you're interested in doing that. But this first sum is 56/3. The second one is -13/6. 56/3 minus -13/6 give us an answer of 125/6. Okay, our next question is to find the area bounded by x squared minus 6 and g of x equals 2x on the interval from -2 to 3. You certainly could find the points of intersection, but I'm going to appeal to the graph. So I'm going to assume that we're going to graph this, see it, and we can identify our points of intersection that way. But if you wanted to solve them, x squared minus x equals 2x would be the way to do that. So you can see we have a point of intersection there at 0. Does that make sense? 0 squared minus 0 is 0. 2 times 0 is 0. That looks good. We have another point of intersection here at 3, where this parabola hits this line. 3 squared minus 3, 9 minus 3 is 6, 2 times 3 is 6. So indeed, 0 and 3 are the points of intersection. You can get them by looking at the graph, or you could just solve the equation x squared minus x equals 2x. But this is a little different because I've told you to use the interval from -2 to 3, the area bounded by these two functions on the interval from -2 to 3. Well, Below this function and above this function from -2 to 0, we have this purple region. And between the functions on the interval from 0 to 3, we have this gray region. So if I'm going to find the total area bounded by those graphs on that interval, I'm going to need to find this first region, I'll call it R1, and the second region, I'll call that R2. Now the region 1, the x values range from -2 to 0. The function that's on top is this parabola. That's x squared minus x. The function that's on the bottom is 2x. That's the straight line. For region 2 is going to range, x values range from 0 to 3. And then which one is on top, which one is on the bottom. The function y equals 2x is on top, and the function y equals x squared minus x is on the bottom. So the total area will be the area of region 1 plus the area of region 2. So we'll need to evaluate both of those integrals. So there's region 1, x squared minus x minus 2x, which would result in x squared minus 3x. So we need to find the antiderivative of x squared. That, of course, is x cubed over 3 using the power rule. The antiderivative of 3x squared over 2, evaluated from -2 to 0. We're going to plug in 0 first. 0 cubed over 3 minus 3 times 0 squared over 2 minus, plug in -2 in parentheses, cubed over 3 minus 3 times -2 in parentheses, squared over 2. That's what it's going to look like. Now this first piece, 0 cubed over 3 minus 3 times 0 squared over 2, that is just 0. This piece, -2 times -2 times -2 is -8 over 3, minus 3 times -2 squared, 3 times 4 over 2. 0 here, 3 times 4 over 2, 12 over 2 is just 6. So that'll be 8/3 plus 6 when we distribute that negative sign. 8/3 plus 6 is 26/3. So 26/3 is our area of region 1. Now 26/3 is just a little bit short of 9. If we count the boxes, could we believe that we get to about 9? Maybe these two together is about 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I think so. It is a pretty good approximation. So counting the boxes gives us an idea to see if our answer is reasonable. But that was region 1. Now we need to go ahead and do region 2. That area is the integral from 0 to 3, the top function, this time 2x, minus the bottom function, x squared minus x. Distribute the negative signs. Be careful. So we get 2x minus x squared plus x. 2x plus x is 3x. Integral from 0 to 3 of 3x minus x squared. Antiderivative of 3x, 3x squared over 2. Antiderivative of x squared, x cubed over 3. We're going to plug in 3, subtract, plug in 0. Plugging in 3, 3 times 3 squared over 2 minus 3 cubed over 3, plug in 0, 3 times 0 squared over 2 minus 0 cubed over 3. And the zeros are nice because everything disappears. So 3 squared is 9, 9 times 3 is 27, 27 halves, minus 27 thirds, 0, 0. 27 thirds, of course, is 9. But let's just go ahead and do the subtraction, and we get 4.5. And let's take a look at region 2 and see if we could believe that that area is 4.5. Well, let's see. All of this together looks like it's about 1. That looks like it's about 2, 3, 4.5. Yeah, I think I could believe that. So the total area is the region 1 plus region 2. That'll give us the total area bounded by those two functions on the interval from -2 to 3. We need to add area of region 1 plus area of region 2. And let's recall what those numbers were. Region 1 was 26 thirds. Region 2 was 9 halves. Adding that together, we get our total area of 79 sixths. And that will conclude this problem.